All right, how many of you, if my slides ever show up, how many of you got lost this morning just trying to find this place? All right, I'm gonna guess it's a lot of you because I can't see any of you, but would a diagram have helped? Like, hey, go here, enter here. Probably, right? That's exactly what this talk is about. Stop drawing pointless arrows. We're gonna be taming complexity with diagrams and waking up my laptop so it actually shows the right screen. So, my name is David Khourshid. I'm at David K Piano pretty much everywhere. Piano's not my last name. My last name is Khourshid, and like was mentioned, I am a piano performer. I studied piano in university. And let's see, what else about myself? A couple weeks ago, I actually just got married. So, and my wife is actually here in the audience. And I mentioned this because we wanted to do something special for our wedding. We wanted to have a first dance where instead of just having a DJ play the song, we wanted our friends to actually perform it live. And this was actually at first a little bit complicated to get all together. You could imagine if some of you are musicians, just getting a group together and just having the same idea of what to play, it could be difficult. Thankfully, there's something called music notation that really helps just groups of musicians organize and just be on literally the same page. And I decided to whip up MuseScore and actually notate all of the music for the group to play our first dance. And it sounded really, really nice. And this is the actual music over here. And yeah, this diagram really, really helped us just all get on the same page. And you might be thinking, wait, is this a diagram? And the answer is yes, and I'll explain that in a minute. So I went to university for piano, and then I decided that, I was playing around with HTML, CSS, a little bit of JavaScript, PHP, things like that. And I got a job at the university, and I learned that being behind a computer keyboard actually paid a little bit more than being behind a musical keyboard. So I decided to go with that career path. But one of the things that always frustrated me, and I'm sure many of you who are musicians here were also frustrated with, is just this code. You cannot read this. Even if I try to zoom in, don't worry about it. It's just, code is linear, right? You read it like you would read a book, left to right, top to bottom, and file by file. But the problem is that programs are not really actually structured this way. Programs are really more structured in a series of connections where it's like we have these modules which are connected to this, and this thing communicates with that. So if you sort of envision it, you just have these lines pointing to just different things, but code is very much linear. And so that was one of the biggest things that bothered me, where with music, we have notation that can actually describe all different types of genres, and with code, it's like there was no visual formalism, at least not one that I discovered when I was a junior developer, that really helped with that. And so that's how I got into diagrams. So first of all, what exactly is a diagram? What constitutes a diagram? There's actually only two simple criteria. One is it's visual, so it's a visual representation of something, and the second is it's helpful. Take this subway map. Or railway, whatever you call it, metro. People have different names for these. It's helpful and it's visual. Music notation, also helpful and visual. So this talk is going to be sort of two different things. First of all, why diagrams are useful, and actually how to make your diagrams even more useful, because we all have probably made diagrams before, but we all have probably made the same mistakes making these diagrams. So I was researching diagrams as a junior developer, just really wanting that visual aspect. I started with flowcharts, which seemed pretty simple, but were a bit limiting in describing just the complex nature of our applications. So then I eventually learned about state machines, and then I discovered state charts, and all of these just sort of stemmed from flowcharts, and I became obsessed with just these ways of representing our application logic at any level of complexity. And I just really wanted to just to have any kind of developer work with their team on visually expressing their application logic. Because the truth is, our software gets more and more complex. we're always going to be adding features, removing features, fixing bugs, making changes, all these things that just make our software super complex. And in reality, we need visual languages to do three things. First of all, we need to understand what the heck our applications are actually doing. We need to be able to communicate all of these processes and flows with our entire team, even if they're non-technical, so that they're on the same page. And we also need to analyze, like actually look at the diagram and spot deficiencies or places where we could optimize, or even logical bugs and things like that. So diagrams are very, very useful for understanding software at scale. Now, I got really interested in this interplay between diagrams and code and how they sort of related to each other. And so in learning about state machines and state charts, I learned about terms like executable diagrams and visual formalisms. So just to give you an idea, a visual formalism, according to David Harel, who created state charts, are a diagrammic and intuitive yet mathematically rigorous language. So it's a visual way of describing a program that can be converted directly to code, and that seemed really, really, really magical to me. Now, I'm not going to assume your ages in the audience, but I know some of you might be reading this and thinking, OMG, is he going to be talking about UML? And the answer is no. I sort of started development after the whole UML thing. I mean, UML is still popular in some areas of tech, but it wasn't really popular, with the startups I worked with. No one ever said, you must create a class diagram and you must generate this code, and here's code that you don't touch. We never used UML to its strictest form. And I think that UML has some good ideas, but really it's just way, way too rigid and prescriptive for what you're trying to do. So really we're going to be talking about UML, the good parts, like just not full UML. Because I think that diagrams can come in basically many different forms when it relates to your software. And these forms are more useful depending on what exactly you're trying to do. So for example, there's diagrams which are purely visual. These might be something you write on a whiteboard. And then there's diagrams where you can actually have a text representation that generates the diagram. So you could think about mermaid, plants UML, things like that. And you could actually put this in source control and actually see the changes. So text to diagram, very useful. And then there's code to diagram, where you could take code and actually generate diagrams from it. This gets closer to UML, but in some cases, this is also very useful for visualizing your system. And then there's this magical bidirectional code to diagram, which this might not be applicable for all use cases, and it does take a lot of work to get right. But in an ideal world, if this works, it is truly magical. And how exactly does this work? Like, how can we even possibly make code to diagram or text to diagram, diagram to code, etc.? The truth is that everything, at least in our applications, is a graph. So, if you try to explain microservices, you might, just go to a whiteboard and start drawing things like this, and you'll quickly understand that everything is a graph at varying levels of complexity. By the way, this is a hilarious video. If you haven't seen it yet, please check it out on YouTube. So what's a graph? We have nodes and edges. So nodes are things, edges connect the things. And this is actually extremely versatile. Our nodes represent entities, which could be components, people, roles, such as like organization charts, components in your system, states in the state machine, etc. And then we have edges, which describe relationships between all of these entities. So these could be state transitions, or how data flows from one entity to another, or things like constraints, distances if you're making a map, or cause effect, like this causes that. The three levels of abstraction that I'm going to demonstrate with diagrams really cover pretty much the entire way that applications are structured. So at the smallest level, where you could even barely see it, we have data. And then we have actors, which really take that data and transform it based on messages it receives. And then we have systems, which describe how these actors interact with each other. So this is my UML, the good parts slide. These are the 3 diagrams which I think are the most important, in my opinion, to learn and to use with software, regardless of if you're using them in a strict way or a less formal way. Just having these 3 represents all of these 3 areas of abstraction. So the first one, of course, is entity relationship diagrams, which, as the name mentions, talks about the relationship between entities that you might have in your system. So, for example, this might be a cafe system where you have customers and orders and things like that, and they're all related to each other. So if we zoom in, you could see that we are describing relationships between customer, order, employee, menu items, inventory, all of that, and also how they relate to each other. Now, these can be loosely structured diagrams where you're just doing it on a whiteboard, or they could be generated, which I'm going to show you a few examples of in a minute. One of the confusing things I found about entity diagrams was these little things, these crow's feet over here. And also, this slide really exemplifies just how simple you can make your entity relationship diagrams. So the 2 lines mean one and only one, even though there's 2. I don't really get the connection, but that's why I honestly just like plain text instead of these weird symbols. And then this means 0 or more, because a customer can have 0 or more orders, and an order belongs to one and only one customer who made the order. So these diagrams are extremely useful for talking about the relationship of data in your application. Now, there's a lot of useful tools that I've used. One of them is SQL DBM, which allows you to visually create these diagrams and actually transform that to SQL code. And I love the aesthetic and how visual it is. And I also love how you could just take this and show it to someone non-technical to describe how the data is related and all of the different kinds of entities that are in your application. Then there's Supabase, which I'm not sponsored by Supabase or anything. I just love using it. It's for Postgres databases. You could take your existing Postgres database and actually generate a visualization of your entire database. They also recently released database.build, which takes it to the next level, where you could actually create applications just by talking to AI, and it will do 2 things. It will generate this entity relationship diagram, and it will also create the SQL code for you, so you could use it directly in your app, which makes sense. They want to make money, so it's like, hey, we built this for you. Click here to deploy it to Supabase and pay us like $25 a month or something. All right, but all this talk, and this is, for example, a coffee ordering app. I was jet lagged for the last week, and I really, really needed coffee. So if I were to just, walk up to any of the great cafes around here and just stand around, the barista wouldn't really know what to do. They'd be like, can I help you? What would you like? So in our daily interactions, we're doing message passing, which sort of alludes to what I'm going to talk about next. But the barista might ask me what I would like. I would say, I would like a flat whites, please. They would give me a flat white, after paying, of course, and say, here you go. And then I would say, thank you. And so this is message passing between 2 actors. And it actually sort of looks like a sequence diagram, which is one of my next favorite kinds of diagrams to use in software development. So with sequence diagrams, we have an actor and we have a lifeline, which is depicted by this solid white line, or dotted. And so the interaction between them are the messages passed from actor to actor. And you can have more than one actor. So for example, if I ask for a coffee and I ask the cashier will tell the barista, like, hey, we have a new order. This person wants a flat white. And then the cashier will ask me for money. I couldn't find the emoji for Australian dollar, so we have a little bit of a mix there. And then I would give them money, and they would give me a receipt. And after some time, the barista would give the cashier coffee in this scenario, and the cashier would deliver it to me. And this represents a complete flow of the interaction between these three actors for the goal of me getting caffeinated and defeating jet lag, which I've almost done. I woke up at 4 a.m. this morning, so I'm getting there. So this has really taught me a lot about the actor model. So this is how sequence diagrams relates to code, where we can actually envision our systems, no matter how complex they are, as sort of an actor model, way of just these things interacting with each other. So in the actor model, we have actors and messages, and all computation is performed inside of a single actor. So basically, an actor, all it does is receive data, and then it does something with that data. It might have its own internal state, and it might change its behavior depending on the message that it received. Now, actors can only communicate through messages, and I really like this part of the actor model because there's this isolation in state, which makes it really easy to reason about just all of the actors in your system. There's no implicit state or global state or anything like that. Everything comes from the actor's internal state and the messages it receives. And so the only way to share data is to send immutable messages to each other, which is really nice. And in response to a message, an actor can do one of three things, or even all three. It can change its state or behavior, which means when I receive a message, I might do things to the data in my internal state, but I might also change how I'm going to react to the next message. What it could also do is send messages to other actors, of course, because actors need to talk to other actors. Every system has more than one actor. Every non-trivial system. And it can also spawn new actors. So you might be thinking like a service can spawn instances of other services, which themselves can spawn other services too. There's many implementations of the actor model, but even if you're not using a language such as Erlang or a library such as Orleans or Xdates to represent your system strictly as actors, you can really envision these parts talking to each other. So you might think, hey, I can use sequence diagrams to represent just how this service communicates with that one, even if it's not strictly an actor model. But I think that the actor model is a really, really useful way of thinking. Now, for actually making sequence diagrams, I really love using swimlanes.io because drawing sequence diagrams is a little bit tough. You have to draw the lifelines and the arrows between them. It's a very nice visual representation, but Swimlanes allows you to create it just in text using a very intuitive DSL or syntax. And also, I created a library called Stately.ai/inspect, which allows you to do something different. It's not creating sequence diagrams. Instead, it's inspecting different components of your app, wherever you hook it up, and actually visualizing the message passing between each of the components in real time. Not sure if this video is playing. Oh, yeah, there we go. It's just taking a while. So yeah, in this case, we're modeling a coffee dispenser or hot chocolate. I forget which one it is. And you can see that messages are actually being passed back and forth and visualized in real time, which I think is pretty nice. There's also appmat.io, where this works for many languages, not just JavaScript or TypeScript. I think it works for Java, Python, etc., where it actually inspects your network connections as your app is running, and it visualizes them in real time. So this is another very cool tool that I recommend you use, just because visualizing these diagrams just brings a whole new level to how your application is working. So you don't have to write console logs and make the diagram in your mind. Instead, you could see it visualized in real time. All right, story time. So there's lots of cruises in Australia, and I live in Florida, where we also have lots of cruises. And how many of you have actually been on a cruise, just on vacation? Okay, so a lot of you. It's sort of a thing in Florida. Everyone who lives in Florida basically goes on a cruise, so I'm thinking maybe it's the same in Australia. Someone told me that Australians love to travel, so totally makes sense whether you're flying somewhere, taking a cruise. But Wi-Fi is really, really expensive. So I remember that I was working, but I also was going on a family cruise, and I'm like, I needed Wi-Fi. So it cost something like $80 a day or something ridiculous like that. And the Wi-Fi system was itself pretty simple, where I would make a request, and first it would check, did this person already register for Wi-Fi? If they didn't register, then I was granted Wi-Fi access for the day. $80 later, I was able to access Wi-Fi. Now, I also wanted Wi-Fi on my cell phone, but of course, I registered with my computer, and so with my cell phone, when I tried to make a request, it sent a message from the clients to the service, was it registered? And the answer was yes, it was, so I didn't have Wi-Fi access. It said, sorry, you're only allowed one device per day. So, speaking of Wi-Fi, all right. So what I actually did, and this was just 6 or so years ago, but I knew of sequence diagrams back then, and I quickly sketched one out on the back of a paper, and I'm like, okay, you know what, how does this system work? Okay, so we have something that's checking whether I'm registered or not, but I want Wi-Fi on both devices, and I don't want to pay for 2 devices. So what do you think I did? Real quick, I made another request while the other one was checking. So basically, I did both my laptop and my cell phone at the same time. And because of the sequence of events, I was able to cause a race condition and get Wi-Fi access for both the devices. Saved myself $80 doing that. All right, so now my favorite, what I think is, and I'm biased, but what I think is one of the most useful parts of UML, which is state machines. Some people call them state diagrams. I know them as state machines. But machine is a very, very intimidating term, even though conceptually they could be pretty simple. For example, we might model that a dog can be asleep, and then on the event that it wakes up, it's awake, and then when it falls asleep, it's asleep, and you can't be in more than one state at a time, unless you were jet lagged like me. But yeah, machine just sounds very complicated, but there's really only 3 core parts that you have to keep in mind, which are states, which again, you can only be in one at a time, events, which help you transition between the states. And so those are the transitions or the arrows between the states. So state machines have a few important parts. We have the finite states. Like I mentioned, you can only be in one at a time. So in this example state machine, we are in the idle state, and when the load event happens, we're loading, and then when we resolve, we're in the success state, but we could go back to loading by reloading. And so this is an important part because it shows that state machines and these flows are not necessarily linear. And that's something that diagrams are really, really good at explaining, is that things can loop back. Things might branch off. Things might have substeps. So that's why I really like state diagrams for explaining processes. Then, of course, we have the events and transitions, which cause the transition between one state and another state. State machines also have final states, which denotes the end of a process. But when I was making more and more complex applications, this actually wasn't enough. So I discovered state charts, which were invented by David Harel back in 1987, and eventually became part of UML. And I sort of discarded the UML definition and went with the regular David Harel paper from 1987. And this was actually in the paper. This is a Citizen Quartz multi-alarm watch, so one of those cool 1980s watches where you could set alarms, set the display mode and everything. And this is the schematic or the diagram for how it worked, which I thought was really cool to see. State charts enable a lot of other things in state machines, and they make them really, really expressive. So one of them is transition actions, where you can actually say, when this transition happens, there is a side effect. So now all of a sudden, you have a declarative representation of the side effects that happen in your application. Because applications aren't just states. Applications are also the side effects that happen. An application without side effects is not useful at all. There's also simplifications like state actions, where we can say, Whenever we enter the state, we're going to fetch data. Whenever we exit, we're going to log telemetry. These can be equivalents to transition actions, but it's just a much simpler way of representing them. Then there's also guarded transitions. So just like a flowchart, we can say only transition here if this condition is true. So only load if we're actually online. Otherwise, we go to the offline state, wait for online, and then we can continue again when we're online. Then there's compound states, which simplify state charts even further by being able to express sub-processes. So for example, when we're loading and the loaded event happens, now we're in the ready states, but we also transition to the initial state over here, which is playing. So you can imagine this is a music player, and regardless of whether we're playing or paused, when you press next on the music player, it's going to first look at the child states and see, is there a next transition? No, there's not. So let's look at the parent. Is there a next transition on ready? Yes, there is. So we're going to transition to the loading state. So you could see, instead of having to draw multiple arrows from each of these states, we can just group them in one parent state and really simplify our state diagrams. There's also history states, which are another interesting aspect of state charts. For example, if we're loading a song and the song's loaded, then we will initially transition to the playing state, but let's say that we press next. And whether we're playing or paused, it's going to load the song, but we want to remember whether we were playing or paused. So that's exactly what history states are for. They let you transition to the most recent child state that we were in. So if we were paused and we load and the loaded event happens, we're going to go back to paused just because that's where we were at. There's also parallel states, and parallel states allow you to further simplify state charts and state machines by saying these two things happen concurrently. So we have the player, which is representing whether we're playing or paused, and we have the volume control, which represents whether we're muted or unmuted. So if you were try to do this without parallel states, you would have to represent these as a combination of states, such as playing muted, playing unmuted, paused muted, paused unmuted, and you could see how it could get even more complex when you have even more different concurrent states that you need to represent. So that's why parallel states exist. One of the things that I really, really appreciate about state machines is how they map directly to requirements. So for example, logged out, log in, logged in. This is a very simple state diagram explaining an authentication process, but it maps to your gherkin, cucumber, whatever you want to call it, given a user is logged in. When the user logs in with valid credentials, then the user should be logged in. And so all of this can be mapped to a diagram. So really, you could think of any application that you create as just a series of these given when thens that each describe part of a path of a bigger state machine. So you could write hundreds and hundreds of different gherkin statements, or you could just draw a state diagram and derive that behavioral logic right from the diagram. And of course, you could just hide the level of abstraction, so you could only, just depending on who your audience is. For example, for developers, you might want to show more information. For non-developers, this might be sufficient. State machines, like I mentioned, also allow you to declaratively represent effects, such as if we're in the toggle state, we want to play a video, and if we're in the, if the toggle action happens, we play a video, and if we toggle from the full screen, we want to pause the video. So that can be declaratively represented here, instead of what we normally think of as just random things that happen in our code base that are very, very hard to track. So side effect management just becomes very declarative with state machines. And so one other great thing about state machines is that since they're executable, you can actually simulate them and see them in real time. If this video plays, there we go. So you can see that we can actually visualize what happens when certain events are triggered. And you could see which state you're in, what transitions to what, and it gives a very visual way of showing the rest of your team basically how your application logic works and it makes it very simple for them, without staring at code, to give feedback on this should work this way, or maybe we can change this, or even just understanding all the features in your application. So some other things I really like about state machines is it makes it simple to identify logical flaws in your application just by looking at the diagram. Now, let's say that your code compiles, there's no type errors, no linting errors, everything just compiles perfectly. That doesn't mean that your software is necessarily correct. Can you see anything wrong with this diagram? Well, we might be missing a few states. For example, if we have this payment form, we might be missing the option to go back, or if we're on the payment state, we might want to give the ability to cancel. And this is something that both developers and non-developers can catch just by looking at the diagram. We can also, like I said, just explain different user stories just as parts of the diagram. But we can go further than that and actually just trace entire flows. So because our state diagrams or state machines are a graph, we can apply things such as shortest path to say what is the shortest path from the initial state to the final state in our application, and just really represent this as the happy path that a user would take in the application. Or we could add more context to it and say, like, oh, what is the shortest path where we actually have to enter a shipping address? And then it would find that shortest path that meets the criteria. So you can imagine that this is useful not only for determining happy paths and flows, but also for testing. And so this is an area called model-based testing, which is really useful. State machines are in game development a lot. And with state machines, you can also represent them in code too. And so that's why I created Xstate, which is a JavaScript/TypeScript open source library for creating these state machines in this JSON-like format that allows you to visualize them as a state machine. And we're not using switch statements because we actually want to take those JSON objects and analyze them so that we could visualize them too. So it starts with create machine, and then you pass this JSON object, which has an initial state, and then a mapping of states, such as wandering a maze or chasing Pac-Man, and then different transitions. So for example, when we're in the wandering maze state on lose Pac-Man, then we go to chasing Pac-Man. And so all of this represents the behavior of, for example, one of the ghosts in the game. And you can either run these in real time, or I actually introduced some new functions which allow you to just get whatever the next state and the side effect/actions are going to be based on the events that you provided. So given we're in the initial state of wandering a maze, when the lose Pac-Man event happens, now we're in chase Pac-Man. And so you can use that in your applications. It's framework agnostic. Use it in the front end, back end. And it just allows you to have your application logic in one place where you could also visualize it at the same time. Now, some of you might have worked with state machines and state charts before, and you might be thinking, you know what? I get the benefits, but I've created some pretty gnarly diagrams before, and they were even confusing for developers. And you might be thinking, like, I thought diagrams were supposed to reduce complexity. The truth is, diagrams actually reveal complexity, and with this, it's actually sort of a feature, not a bug, where diagrams just show you all of the parts interacting with each other, but that doesn't mean that diagrams necessarily have to be complex. Take this famous one from Slack. I'm sure some of you have seen this before, right? Where this is the Slack flowchart for determining whether to show a notification or not. So first of all, Slack is very complicated. I'm still learning it, and I've used it for many, many years. But imagine this in code. Imagine that you didn't have this. The code is probably much more gnarly than this simple in comparison flowchart. All right, so how do we make good diagrams then that don't confuse people? Well, we start with intention. What is the reason why we're creating this diagram? Like I said before, diagrams are meant to be visual and helpful. So we want to help people. And so you have to think, am I doing this to explain how the intricate technical processes work in this application, or just to give an overview of like mapping these user stories to these specific flows? And then that really depends on the audience. So your diagrams for developers might actually look very different than your diagrams for designers or project managers or other stakeholders, where they might be more simple or show things at a different level of abstraction. And so that's why, given the intention and audience, you also have to determine the scope of your diagram. What do you want to include? What do you want to omit? And so in general, intention answers why are you making the diagram, audience determines who you're making the diagram for, and scope determines what is going to be included in this diagram. So when you're making a diagram, I want you to actually do, just before you start putting pen to paper or start making the diagram, just fill out this Mad Lib where you say this diagram is for which audience, and it is to help whatever the purpose is, and it will cover these things, but it will not cover these specific things. This simple statements can accompany any diagram you create, and it's going to make it very clear to whoever's reading your diagram what the diagram is about and if it will help them. So, like I said earlier, making diagrams is really easy. We probably all have done it before, but making good diagrams takes a lot of practice. And trust me, I've been making state machines for over 10 years now and just drawing these diagrams, thousands and thousands of these diagrams. And I've also seen a lot of diagrams. I worked at Microsoft, so they were all over the place in more than one way. But yeah, making good diagrams takes practice. And I feel like there's a lot of obvious and non-obvious mistakes that we make in making diagrams. So the first one, unlabeled objects. You've probably seen diagrams with like these random symbols everywhere or these colored boxes or something. And they're just pointing to each other. And this might make sense in whoever made the diagram, but really it's very confusing. It does not take much effort to just add some text describing what these objects are. And in a similar vein, pointless arrows. Now, all arrows technically have a point, but what I mean by pointless arrows, and this, trust me, look at the diagrams after this talk that you yourself have created or received, and you will see so many pointless arrows where it doesn't mean anything. It's just pointing from one thing to another thing. The meaning might be implied, but really, it doesn't take much effort to just add a label to your arrow to describe what exactly it's for. There can also be too much detail in the diagrams, and again, this can be solved by answering those three questions. What's the intention? Who's the audience? And what is the scope of the diagram? This is an example of even using our software at state.new, where the state chart was just too big and it was showing just way too much. This is a generated diagram of Netflix's microservices, and you can see it's way too much info. It's not really helpful at all. Sort of looks like coronavirus. And then we have too little detail. And you've probably seen these diagrams before where it's like, hey, it's simple. This talks to this, magic happens, and voila. In fact, this is happening today with all of our LLM agentic applications where we think, okay, here's a prompt, and some magic happens, and then the AI spits out a result, even though in reality, there are so many steps happening in between, and it's worth knowing what those steps are. So again, depending on the intention, audience, and the scope, you might want to show a little bit more detail depending on who you're working with. I've also seen this recently, mixing diagrams, where, for example, we might be explaining a process where we're in a coffee shop, the barista is idle, we make an order, the order is received, and then through some magic, this order goes to some database so that we have a list of these orders later. And that might make sense, but these two arrows mean two completely different things now. One of them is a state transition, and the other one is data flow. So it might actually be better to explain these as two different types of diagrams, where we go from idle to order received, and we send the order to a database, and then we could use a sequence diagram to show the interaction between the client and the database. Another one is diagrams that are hard to follow. And this one really, really takes practice because this is a simple example, but with larger diagrams, it becomes a lot more difficult to make it look nice. So here we have arrows crossing everywhere. We have states all over the place. We don't even know where to start. And honestly, if you could just answer the question, where does this diagram start? That is the first step to making your diagrams a lot easier to follow. So in this example, we could actually rearrange this like this. So there's two big things happening here. The first one is we're arranging our boxes, our things, in reading order. And so the first one, because we read from left to right, at least here in other cultures it's right to left, same rules apply, but we will start with the first state because it's at the upper left. And then we will go to second, and then we follow clockwise. So we could go to third and to fourth, or you could just follow reading order in a zigzag way, or if your screen space allows, all of it can be in one line. The second thing is that our arrows are no longer intersecting. Now this might be impossible to do, but really your goal is to minimize the number of intersections of your arrows. So you want to clean up the graph by having good alignment, reading order with your boxes, and also minimizing the intersection between the arrows. There's also symbol and color overuse. And so with this, all right, here's an example diagram that I saw, just found randomly online. Now, this makes sense. At least the labels are arrowed. Sorry, the arrows are labeled. I'm getting confused myself. But you could look at each of the boxes. There's so many colors, and each of the boxes have lots of symbols on them where it's just very hard to determine what do those symbols even mean, and are they even useful in the graph. Here's one from Microsoft, and this is actually recently made, just explaining the Azure OpenAI service boundary, so how Azure and OpenAI work together. And there's a lot of crazy things happening in here. Some of the labels are arrowed, some of the arrows are labeled, some of them are not. We have some things in boxes, some things not in boxes. We have one box with an orange border, a dashed orange border, which we don't know why that's special. What does that mean? And then we have this cluster F over here. Like that could be simplified. It just makes things more complicated when they're crossing. So I don't have much time left, but I do want to explain that there's a lot of tools that you can use. Some of them are the usual suspects, like draw.io. You probably use things like Lucidchart and Miro and things like that. I really like using TLDraw just because it's a very versatile and simple whiteboard. There's text-based tools such as PlantsUML and Mermaid Chart, and then there's tools that do both like Stately, and I also really love Whimsical too because it allows you to express many different types of diagrams. But I am going to reveal to you my favorite tool, the tool that I think is the best diagramming tool. And the answer is pen and paper. And the reason, there's a famous study from 2014 by Mueller and Oppenheimer, not the atomic bomb Oppenheimer, he's dead, but a more recent Oppenheimer. And in this study, it was actually shown that writing your notes really activates three parts of the brain: the motor cortex, the somatosensory cortex, which is that tactile feedback part, and the visual cortex, which is the visual representation you see once you make those movements, that because you're activating more of the brain in doing that physical activity, you actually retain more information and get more understanding of what you're doing. So really, just making diagrams physically really, really helps a lot. And so Figma is a great tool for collaboration too. So again, two things that could really help improve the way you make diagrams: making it physically, and also collaborating with your team. So again, I really like using FigJam for this. But in general, tools should never constrain the thinking process. So you shouldn't be limited to what your tool can do. And there's two really good books that have influenced how I think about diagrams. One of them is constructing the user interface with state charts, which really goes beyond state charts and explains how these visual diagrams are useful in thinking about your software architecture. And the second one is Stock Diagrams Help, which I actually brought in this trip. Very visual book, very easy read, and something that I recommend to all teams. It doesn't cost too much. Unlike this book, it costs $725. Don't buy it. It's only like this because it's out of print. Maybe you could find it elsewhere online, but it's a really good book. But yeah, in general, a picture is worth 1,000 words, and a diagram, at least to me, is worth 1,000 lines of code. And if I want you to take anything away from this talk, label your arrows. Thank you very much.